Good morning, this is your Stat Sensei, Mr. Spensei, and we are going to go through the death packet problems 1 through 10 in this video. So, what happens to a T distribution as the degrees of freedom increase? Well, first off, as degrees of freedom increase, if we started off with a T distribution that initially looked like this, the area under the curve is still 1, the means will remain the same, but if we increase it, the new one could look something like this. It'll have exactly the same mean, but it becomes narrower. All right, so the center remains constant, the center doesn't change, and the area and the tails, well, we had a lot of area initially and they decrease. All right, so the answer is they decrease. The center will not change. Okay. A researcher studying the sleep habits of teens will select a random sample of N teens. So this is my sample size from the population survey. The researcher will construct a T interval to estimate the mean number of hours of sleep that the teens in the population get each night. Which of the following is true about the T distribution as the value of N decreases? So if it decreases, that means we started off with the red one and we went to the blue. The center remains the constant, but we ended up with more area in the tail. Center decreases, no. Center decreases, no. Remains constant, and the area in the tails remain constant, no. Area in the tails increased. The center remains constant, yes. And the area in the tails decreases, no. We went from this is if this was 40 and we went to 20, we get fatter. All right. The center of the tails remain constant. Yes. And the area in the tails increases. Yes. Okay. So as you increase sample size, it gets tall and skinny. As you decrease sample size, it gets short and fat. Which of the following correctly compares the T distribution and the Z distribution? Please remember, they both have the same center, but there's more area in the tails for the T distribution than the Z. For small sample sizes, the density curve of the T distribution is not symmetric. Nope, they're both symmetric. For large sample size, the density curve is not symmetric. Nope, they're both symmetric. It doesn't matter the sample size. The T and the Z are both symmetric. The curves of both are symmetric, but the height of the T distribution is taller. No, the height of the T distribution will never be taller than a Z. It'll get close to the Z, but never get there. The area in the density curve of the T distribution is greater than the area under the density curve for the Z. No, it's a valid probability distribution. Both of them have an area equal to 1. All right, that leaves E. The density curve of the T distribution is more spread out. Yep, it's more spread out than the density curve of the Z, especially for small sample sizes. The smaller the sample size, the more spread out the T is. So the answer choice to number 3 is E. Number 4, the distribution of age for players of a certain professional sport is strongly skewed to the right, with a mean of 26.8 and a standard deviation of 4.2. All right. So our mu is 26.8. Our standard deviation is 4.2. Consider a random sample of 4 players and a random sample of 50 players. Which of the following is true about the sampling distribution of the sample mean? All right, sampling distribution of the sample mean. So I'm going to do the 4 and the 50. Sampling distribution of the 4 is going to be the 4.2 divided by the square root of 4. For the 50, it's going to be 4.2 divided by the square root of 50. So this one is still remains skewed, but this one, because n is greater than 30, will become normal through central limit theorem. Both will be skewed right. No. Both will be skewed right. No. Both will be approximately normal. No, this one will not be a normal. Only the sampling distribution for size 4 will be normal. Nope, that one will not be. Only the sampling distribution for size 50 will be normal, and the mean for both will be 26.8. Remember what I always say, the mean is the mean is the mean. We're good with the mean. It doesn't change, okay? And I mean that. Number 5. Which of the following is a true statement? Tests of significance are designed to measure the strength of evidence against the null hypothesis. Well, that's true. That's a true statement. A well-planned test of significance should result in a statement either that the null hypothesis is true or that it's false. No, we never prove truth. We never prove innocence. So that's false. The null hypothesis is one-sided and expressed using a less than or greater than. No, the null hypothesis will always be expressed with an equal sign. So that's false. When a true parameter value is farther from the hypothesis value, it becomes easier to reject the alternative. We never reject the alternative. We reject the null. If this is said reject the null, that would have been true, but it says alternative, so it's false. E, increasing the sample size make it more difficult to conclude that an observed difference between observed and hypothesis values is significant. No, if you increase the sample size, it's easier to reject. That is known as power. As n goes up, power goes up, and it becomes easier to reject. So that's false. The only answer that was true was the first one. A guidance counselor is interested in comparing GPAs of students with home access to the internet students who do not have this access. She pulled the files of a simple random sample of 10 students who do have home access to the internet and a simple random sample of 10 who do not, and proceeds to run a t-test to compare the mean GPAs of each group. Which of the following is a necessary assumption? All right. We're going to run a t-test, and it says the population standard deviations from each group are known. Not necessary because we're running a t. This would be true if it were a z. The population standard deviations from each group are unknown. Not really a requirement, but we'll put a question mark, see if there's a better answer. The population standard deviations from each group are equal. Not a requirement. The population of GPA scores from each group is normally distributed. Bing, 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 bing. That is our best answer. All right. We need to have, they have to be normally distributed. Otherwise, we can't do it because we have a small sample size. If n had been 30 or larger, we wouldn't care if it was normally distributed. But since it's not, we do care. Two confidence interval estimates from the same population, should say, from the same sample are this. One estimate is 95% and the other is 99. Which is which? All right, so here's what we need to do. Let's go ahead, and it should say from the same population, not from the same sample. Same population. Not that it makes a big difference in the problem, but 77.8 minus 72.2 is 5.6. So this ends up with a difference of 5.6. And this one, the other one is 78.7 minus 71.3. And this is 7.4. Okay, but here's what we know. They came from the same population, so they should be the same. Actually, you know what? This could be sample. It'd be fine. We have the same sample, so we're gonna have the same center. We should have the same center, but one of them is more spread out. The more spread out it is, the greater the interval. So as the confidence level goes up, the interval gets wider. All right. So this one is wider. So this is the 99%. This is narrower. So this is going to be the 95%. All right. The 72 point is a 95%. The 72 point isn't, so this one's false. This looks pretty good. This one says it can't be answered. Nope. It came from the same sample. Nope. Nope. The only answer is A. So number 7 is A. I'll back up on that in just a second. Because both of them came from the same sample, that's why I was like, I should say sample. The sample sizes are the same. They'll have the same sample standard deviation because they came from the same sample. All right. So, and then of course, E is just a restatement of combining C and D together. The only one that's true is A. Two 95% confidence intervals are obtained. All right. If the sample sizes are the same, which has the larger standard deviation? If the sample sizes are the same, which has the larger sample size? Okay. So we're going to pretend that they came from the same spot. So let's take a look at this. We have 78.5 and 84.5. So let's subtract those. 84.5 minus 78.5. And this has a width of 6. Then we have 88.2 minus 80.3. And that has a width of 7.9. So this one is wider. All right. So if the size is the same, which has a larger standard deviation? Larger standard deviation means it's more spread out. So this one, the second one, would have a larger standard deviation. So A has to be the second one. So that gets rid of these. I'll mark it like this. As standard deviation goes up, we have it gets wider. All right. The next one. If the sample standard deviations are the same, which has a larger sample size? All right. As N goes up, the width goes down. All right. Well, this one has a narrower width. So if they have the same standard deviation, then that means this one has the larger sample size because it's narrower. So our answer choice to 8 is C. As N goes up, the interval gets narrower. And the reason being is when we look at our formula, we have X bar plus or minus T star S divided by square root of N. If S gets big, the standard deviation gets big. I'm multiplying by that, so I get bigger if that's bigger. The sample size I'm dividing by. If I'm dividing by a bigger number, it's going to get smaller. All right? In general, how does doubling the sample size increase the confidence interval size? Well, let's just say I have my formula, X bar plus or minus T star S divided by the square root of N. And instead of N, I'm going to say it's X bar plus or minus T star S divided by the square root of 2. Well, what am I doing? Well, what's the square root of 2 first off? Let's figure that out. 2 raised to the half power. Oh, 1.414. So I could have rewritten this as X bar plus or minus T star S divided by, not the square root, but 1.414. I'm going to rewrite that because I did that poorly. X bar plus or minus T star S divided by 1.414. Oh, what did I say I was doing? I'm dividing by 1.414. That's my answer. Dividing by 1.414. Because the square root of 2 is 1.414. All right. In a recent study of 1,215 randomly selected middle school students revealed that the average number of minutes they spend on homework during the school week was 180. All right. Oh, excuse me. X bar is 180 with a standard deviation of 45. Which of the following is the standard error in minutes of the sampling distribution of the mean number um, of minutes spent on homework per week for all middle school students? Well, we need to consider our formula for a confidence interval. Okay? So when I look at this part right here is the margin of error. Well, they didn't ask for that. They asked for the standard error, which is S divided by the square root of N. Well, they said 45. And over here, they told us in the very first sentence that it was 1,250. So 45 divided by 1,215. So the one that has that is D. So our answer choice number 10 is D. All right. Appreciate you watching. Hope that helped. Look forward to seeing you on the next one. Thank you.